I've been visiting. I'm visiting Columbia this year, so it wasn't a big trip to come out, but it's still, it's a little bit of a hike, but it's nice to see everybody and good to be back. What I want to talk about today is a very, very classical problem. It's been around for a long time, and I think the interesting thing about it is that the hard part actually turned out to be a fairly low-dimensional question that was open for a long time, and probably well, we'll see what the interesting aspect of the story is that made it possible to solve it in the last few years. I'll put some references up to give a sense of the history of the subject. The original question about studying manifolds with basically constant, in some sense constant curvature, was studied by Cartan and Münzner. I'll say more about what the isoparametric surfaces are, hypersurfaces are. There was some developments in the 70s and 80s, a discovery of new examples that people were not really expecting for a long time. But then the interesting question of whether or not you could actually do a classification came up, and it turned out that it was a harder problem than we originally thought, and it splits into two things. I will say more about how that split occurs, and so the background. Curvature-homogeneous Riemannian manifolds. You say that a Riemannian manifold is curvature homogeneous if for any 2 points there's an isometry of the tangent spaces that lines up the curvature tensors. So essentially to second order, the manifold looks homogeneous. That is the first piece of information you actually get that distinguishes you from flat space is the Riemann curvature tensor, and that's second order. And this basically says it looks the same to second order everywhere. That's what curvature homogeneous means.
So for a surface, what does that mean?
So I'm gonna say that. The obvious example is if you have a homogeneous Riemannian manifold, then it's curvature homogeneous. That's pretty clear. And in dimension 2, the converse is true. That is, if for a Riemannian surface to be curvature homogeneous, it has to have constant Gauss curvature, because that's the only component that there is in dimension 2. And by a theorem of Mending, two surfaces with the same constant Gauss curvature are locally isometric. And so in particular, they're locally homogeneous. There's only one model for any given curvature. Right?
This is a redundant question, but when did Riemann define the Riemannian geometry?
Well, this was 1854, this famous lecture. Well, Gauss had, of course, discovered the Gauss curvature back in the 18, very early, 1820 something, and it was Mending, who I believe was a student of Gauss, who proved that for surfaces anyway, the curvature completely determined it. If the curvature was constant, then the two things, they were locally isometric.
The geometry was defined for surfaces before Riemann.
That's right. Yeah. I mean, it was Riemann who actually defined the Riemann curvature tensor, this R that I've been describing. But the two-dimensional case is only one component, and Gauss was the one who realized that it was an intrinsic quantity to the surface, to the metric of the surface.
Sorry, I'm trying to understand. So, the curvature homogeneous. Do you need a global diffeomorphism?
No, locally, and it's for any 2 points, there's a isometry of the tangent spaces that lines up the curvature tensors. So it's only so it's infinitesimal to second order. It says that the metric looks the same to second order everywhere. But the converse is not true for n greater than or equal to 3. There are plenty of curvature-homogeneous 3 manifolds that are not homogeneous. And in fact, the local classification is it takes some work to understand. You know, just like Gauss started with surfaces in 3 space, a natural place to start in understanding these things is to look at hypersurfaces in a space of constant curvature. This Qn plus 1 sub c is the space form of constant curvature. When c is plus 1, this is just the sphere. When it's minus 1, it's hyperbolic space, and so on. You say that a hypersurface is isoparametric if the eigenvalues in the second fundamental form are constant. Because as we'll see, that implies curvature homogeneity. But by the Gauss equation, if you have something that's isoparametric, it has to be curvature homogeneous. And in the 30s, Cartan, and then in the 40s, Münzer provided many examples of homogeneous hypersurfaces that should be Qn in the n plus 1 sphere, and because they're homogeneous hypersurfaces, they're in particular. Homogeneous means there's an ambient isometry, a group of ambient isometries that acts transitively on the. So it's literally homogeneous everywhere, right? And so anytime you have a group action that has cohomogeneity 1 on the sphere, you'll get a isoparametric hypersurface in particular.
You have to go to at least 4 dimensions to see that?
Yeah, right.
To see something new?
Right, to see something new, right. And in fact, in 4 dimensions, interestingly enough, that's the first place you can see something new, and it was the last place to know what the answer was.
Oh.
Interestingly, as I'll get to. But in the mid-70s, Ozeki and Takeuchi constructed some inhomogeneous isoparametric hypersurfaces. That is, the eigenvalues of the second fundamental form are all constant, but they're not actually orbits of groups. But they constructed them for fairly large values of n. There were no low-dimensional examples.
Just to make a logical point, you have these 2 definitions, and then the homogeneous, the 3rd definition.
That's right.
So, but one is like saying the space is the same second derivative at every point.
Right.
And the other is saying submanifold has the same second derivative that includes the tangent and the normal.
That's right. Yeah.
With the 2
That's right.
Okay.
Exactly. Right. Right. And in fact, when you got in low dimensions, Tsukada proved that every curvature homogeneous hypersurface of dimension 4 or higher is isoparametric. Is actually isoparametric. In other words, the eigenvalues of the second fundamental form all have to be constant, and it's either isoparametric or it has constant curvature c, or there was a particular example that was curvature homogeneous but not isoparametric or constant curvature in.
I'm losing the definitions. I'm losing the definitions.
Okay. Right, so isoparametric means that the second fundamental form is basically the same everywhere.
It's curvature homogeneous.
Curvature homogeneous means that the Riemann curvature tensor is the same everywhere.
Intrinsically.
That's right. And remember, the Gauss equation tells you that the second fundamental form determines for a hypersurface determines the curvature tensor.
Oh, I forgot that.
Right. And so So isoparametric implies curvature homogeneous, but curvature homogeneous does not imply isoparametric, right? Even for hypersurfaces, although it's very close in the sense that as soon as you get to dimension 4 or higher, there's not much possibility to be curvature homogeneous and not isoparametric.
So the counterexample is very precise.
That's right. Yeah. Right. And this particular, he found one example in dimension 5 that was not isoparametric and didn't have constant curvature, that was curvature homogeneous. But he couldn't figure out what happened in dimension 4. That is, for a 3-dimensional manifold sitting in S4. As we'll see, that's turns out to be a tricky question. But he did show that if it's in a space form of constant curvature, of 0 curvature, then the only way to be curvature homogeneous is to be isoparametric.
Is there a lot of juice in the last 3 lines?
Yeah.
Is there is there a global version of being curvature homogeneous? Like, is there a way to glue together all these different isometries in the different spaces?
Not really. I mean, for the following reason, simple thing. If you look at a compact Riemann surface of curvature -1, then that's curvature homogeneous, but it generally has only a finite number of isometries at most,
but I'm not
right?
saying that it should be integrated into an isometry. It could be a section of another bundle. But, is there a way of saying that these isometries of the different tangent spaces very smoothly inside those?
If it's locally homogeneous, then you can look at the set of isometries in the product, and locally, you'll get a what's called a local Lie group in that
That's still
identifies
kind of
them.
Closed or locally exact.
It's local, yeah,
But
right.
I'm saying if you didn't ask for this exactness, do you embed like the exact things, the diffeomorphisms into some space of sections of something? Is that how you study this problem?
I'm not sure I understand the question completely. I mean, exactly what you're asking. If it's actually locally homogeneous, then
Curvature homogeneous.
well, it could be curvature homogeneous, but not locally homogeneous, right?
But I'm saying, is curvature homogeneous determined, like, you're saying curvature homogeneous means there's a map that identifies the curvature tensor
At 2 points. It's only infinitesimal, that's right. Right.
Can there be a section of a bundle of these maps that identifies all the curvature tensors at once? In other words, does it map very smoothly?
Well, you could. I mean, once you fix the curvature, you could look at the set of all frames in which the curvature looks like one particular thing, and that'll give you a reduction of the structure group of the manifold. It'll give you a sub-bundle of the full frames, right?
But it's not what you use to study.
It's well, that's an ingredient because you have to understand what that thing looks like, right? Yeah, but it's and in any case, even this sort of what you might think of as the most restrictive thing, the isoparametric examples, that's been a long process is understanding those, because once they knew that they didn't all have to be homogeneous, it turned out that there were lots of constructions using spinners and Clifford algebras that you could construct examples of these inhomogeneous isoparametric examples. But it was known already from the work of Cartan and Münzer that there were essentially a finite number of possibilities in terms of numbers of distinct eigenvalues you could have and what their multiplicities could be. You can sort of bring it down to in some sense, a finite problem. But then in each case, specifying the multiplicities of the eigenvalues and how many there are gives you a list of problems to solve. And gradually over the years, and really up until fairly recently, they had winnowed down the list of unknown cases to just a few. And while I think there's still some questions about these last cases of 6 distinct eigenvalues with multiplicity 2 everywhere, I think there's still some questions about those particular high-dimensional examples where people are still somewhat concerned about the details. But I think it's mostly people feel like it's mostly done. But there's some pretty, I myself cannot vouch for the details in those calculations. There's a lot of them and a lot of cases. But the thing that was intriguing to myself and Wolfgang Ziller and Louis Florit, who are my coworkers in this project, was this thing was Tsuchada's, the gap that Tsuchada realized, which was the case of hypersurfaces in the 4-dimensional space forms was not solved. And the problem, as I'll explain what the problem is here in a few minutes, the problem turned out that it's an overdetermined problem, but it's not so overdetermined that it's completely rigid. And as a result, there's a gap where some new method has to be introduced, and that's what I want to talk about. Right. So let me go back to the basics to talk about what happened there. If you have a hypersurface, n-dimensional manifold in n+1 dimensional space form, it has of course the first fundamental form and the second fundamental form, and the eigenvalues h1 up to hn are the eigenvalues of the second fundamental form. They're the things we've been talking about. And the Gauss equation tells you that the Riemann curvature, if you know the eigenvalues of the second fundamental form, then you know the Riemann curvature tensor. It has an explicit expression like this that's just quadratic in the C is the ambient curvature, and then it's C plus the products of the HIJs times sort of the constant curvature Riemann curvature tensor. It's a simple distortion of the constant curvature Riemann tensor. This famous the curvature tensor of the Euclidean sphere. Anyway, in other words, if it's easy to see that if this n-manifold, this hypersurface is curvature homogeneous, then the pairwise products of the Hij have to be constant for I not equal to j. And of course, so they have to be constant. But of course, the individual HIs don't have to be constant unless. And here's where the difference in 3 and higher goes. If, of course, if 3 or more of the HI are non-zero, then this condition implies that the HI are all constant. It's just simple algebra. And then it's isoperimetric. And that falls into this classification of the isoperimetric hypersurfaces. And if all but one of them is 0, then it's then of course the Hij's drop out completely, and it's just the constant curvature Riemann metric, right?
So this space form means these 3 things in each dimension.
Yeah, that's right. So now there's hyperbolic Euclidean or elliptic, right? And so the only case, and those are the two cases that Sakata pointed out, that you got the isoparametric case and the constant curvature case. But what happens if two of them, so if it's not isometric or a space form, then exactly two of the HI are non-zero, and their product has to be constant. That's the only way it can happen. So essentially everything is known except in that case, right? And when the dimension is at least 4, the condition that all but two of the HI be 0 while the non-zero pair have constant product is so overdetermined that that Sakata was able to just write down what the possibilities were. To do that.
Is there any hope in codimension 2?
Sorry?
Is there any hope in codimension 2?
Codimension, there are a lot more curvature homogeneous things in codimension 2 for one thing, there's already so many homogeneous things in codimension 2 because there's a huge number of codimension 2 orbits of groups in spheres, for example. I mean, it's not impossible, but it's going to be a large part of work in doing in basically Lie groups, classifying what happens in Lie groups, and but when n is 3, that is, we're looking at a 3-dimensional submanifold of 4-dimensional space form. The condition's overdetermined, but not by much. And overdetermined PDE is something that we have methods for attacking, but there's the standard thing, the classification. When you have an overdetermined system, there's a question about whether or not it's what's called formally integrable. Which means basically that every k jet of a solution can be extended to a k+1 jet of a solution. In the formally integrable case, we have this notion of involutivity, but it turns out that this pair of second-order equations for a 3-manifold sitting in 4 space is not involutive. That is, it's not formally integrable. And so when you look at it, it's not even clear there are any non-trivial solutions. And I think the money was on the idea that in fact there would not be any examples, any non-trivial examples in dimension 4. Nobody had seen any, and so people thought, well, if there really was such a thing, then we would know about it already, because it's in such low dimension, right?
That's risky.
That's risky. That's right. Anyway, so let's look at the 4-dimensional case. That is hypersurfaces in 4 dimensions. The standard model in sitting as a hypersurface in R5, Sakata had already shown that the flat model in dimension 4 couldn't have any exceptional examples in it. So we're only caring about positive curvature and negative curvature. And so there's basically 2 cases. There's the sphere and the hyperboloid. Right, hyperboloid of 2 sheets, and if you
Went like this.
I went like this, but I should have gone like this. Right, you're right. Yeah. Standard orthonormal basis is orthogonal, and the first one might be, or the 0th one might be plus or minus 1 in its inner product, but the others are plus 1. And if you have a hypersurface, then what you want to do, of course, is in the usual Darboux moving frame, is choose E0 to be the position vector of the hypersurface, and then E1, E2, E3 tend to span the tangent space, and then the E4 will be the normal. And you can write down the structure equation for this, that in that case the differential of E0, the differential of the position vector is a linear combination of the E1, E2, E3, and so on. And these are the eigenvalues of the second fundamental form. E4 is the Gauss map. That's the picture. And it's understanding what the possibilities are if the possibilities are one of these h's has to be 0 and the product of the other two has to be constant. That's what that's the condition for that's the two equations that determine these hypothetical hypersurfaces. Yeah, there's anyway. To be curvature homogeneous, like I said, means is there a oh well, I can do it this way. To be curvature homogeneous means that one of the eigenvalues is 0. So go ahead and leave that way, and then you can see the eigenvalues of the Ricci tensor are, if H1 and H2 product to be some constant, then the eigenvalues of the Ricci curvature are 2c, 2c plus a, 2c plus a. You can easily work that out from the formula that I wrote down earlier. And the interesting thing that I want to bring up in this case is that because H3 is 0, that means that this guy is 0, which means that the differential of E4 is a linear combination of E1 and E2. In other words, the rank of E4 mapping into Q4 is 2 everywhere. So its image is a surface sitting inside the dual quadrant. And in fact, from this you can also see, or you can immediately see, is that since the differential is a linear combination of E1 and E2, then for every point in this image surface, it turns out this point E0 lies in the normal 2 plane to the surface, because the tangent space to the surface is E1, E2 at the point. So E4 lies in the normal 2 plane, and
the geometric picture.
The geometric picture is like this. That the geometric picture is this: that you have this hypersurface sitting inside. Let's think of the 4 sphere. You have a hypersurface which is 3-dimensional, but at each point, I should draw it. Unfortunately, I can't really draw it, the dimensions right. But the point is that at each point the normals. If you look at the normal to the surface, that actually gives you only a surface, not a as E4 varies, it gives you only a surface, and so the normal to the 3 manifold at each point, the normals only fill out a surface. They're not 3-dimensional. Right? Because of that 0 there. And the important thing is that E0 is perpendicular to
the cylinder in 3 spaces.
Yeah, so
The normal will fill up.
right. So essentially what it means is that E0 actually moves on a circle, on a great circle, that a great circle of points that all have the same normal. So the surface is actually foliated by great circles. I mean, the 3 manifold is foliated by great circles. And so exactly and the fibers are the points that all have the same normal at each point.
Bundle over some.
It's a circle bundle over a surface. That's right. Yeah. If you have a three manifold sitting inside, let's just say S4, and there's a circle bundle over this surface, which which also maps into S4, and the normal at each point factors through this, right? So you get the image here is a surface. The image of the normals gives you a surface, and the fibers of this map that give you the normals are great circles in the.
But if it's not S4, then the sigma is not in S4.
Sorry?
Sigma is always in S4.
Sigma is in S4, right? Right.
Hyperbolic.
But that's right. Well, it's in the dual quadric, right? Right. And the point is that, and conversely, the point is that if you just think of this surface sitting in S4, what are these points? These points are actually the unit normal bundle of the surface. So this guy is now identified as the unit normal bundle of the surface, right? So the geometry is really the geometry of a surface. That's the point.
Is it a torch?
Well, the image that in fact we want to know what that surface could be, right? And we're going to find out. Right. So the point is that our original three manifold is just an open subset of the unit normal bundle of a surface sitting in 4 space. And so the problem reduces to classifying the surfaces in this dual quadric whose unit normal bundle is curvature homogeneous. That's what it amounts to. So this is some overdetermined system of equations for this surface. So it really, in spite of the fact that it looked like a three-dimensional problem, it's really a two-dimensional problem. But it's an overdetermined PDE for a two-dimensional problem. This.
Can I ask just one? So the circle bundle doesn't have like a underlying linear structure or anything like that.
Well, there are great circles in the 4 sphere, say, and so they do have a natural. I mean, they're circles in a vector bundle. I mean, they're unit.
So that
things.
S1 bundle is actually.
Yeah, that's S1 bundle. Yeah, right. Yeah. So there's not anything mysterious about that. So anyway, so I copied up the left invariant form that shows up that encodes all the geometry in the structure equations. I just copied that up, and of course because of the equation dE equals E times this theta. Theta is E inverse dE. So you get the structure equation, d theta is minus theta wedge theta, right? And everything can be recovered from using that identity. Well, this by itself would be, is involutive. That's determined. But we're not considering an arbitrary theta. We're considering only thetas that look like that, right? So it's PDE for the theta to look like that, right? And in fact, it turns out that using the Cartan identity, and here's where I don't want to get into too much detail because I only have so much time to talk about it, but using this, it turns out that if you know A and the two one forms, H1 omega 1 and H2 omega 2, you can actually reconstruct all the other forms by just by just writing out what this equation means and what it determines, and all the remaining entries are determined. Of course, I'm assuming we know C as well, which is either +1 or -1. So in some sense, the unknowns are A, eta 1, and eta 2. And of course C, which is fixed, is +or -1. So you can determine them all, and in fact,
Does H1, H2 will multiply something?
yeah, H1 is a function.
H2 multiply omegas.
Yeah, so omega is a one form. Omega 1 is a one form. So H1 omega 1 is a one form, and H2 omega 2 is a one form. They're all one form. Those are one forms on the surface. H1 and H2 are known.
Well, then you have omega 1 wedge omega 2. That's multiplied by H1, H2. Take the product of those two one forms.
Yeah, you could take those. Well, that's the area form on the surface, right?
H1, H2.
Right. Yeah. So if you think of these as being given, they're enough to reconstruct everything else in the form theta, but they actually, because of this equation, there's still some conditions left over after you've found all the others, after you've determined what the other unknown quantities are, and the conditions that are left over look like this. The conditions tell you the exterior derivatives of the etas in terms of the etas and two functions P1, P2, and I'll just say Cartan's identity implies that in order to this to hold, there have to be functions P1, P2, P3, P4 so that these equations hold, where P1 and P2 and P1, P2, P3, P4 are determined by differentiating H1 and H2. I don't want to give the formulas because the formulas are somewhat complicated and will obscure the idea. But so you have, think of it like this. You have these unknowns, eta 1, eta 2, P1, P2, P3, P4, and you have differential equations for them. That is, you know their exterior derivatives in terms of these known quantities, the functions and the one forms, the 4 functions and 2 one forms, where this F is some explicit set of rational functions in the 6 entries. And the HI are explicit rational functions of these things, right?
Suppose you wanted to construct M3 extrinsic,
right,
abstractly, without it being embedded.
Right. Well, you would be able to construct it abstractly from this data.
You would?
Yes. Right.
Not the embedded.
Well, up to being able to integrate ODE. You could reconstruct the embedding too. If you can integrate ODE, then you could reconstruct the embedding as well. That's the structural equations give that to you, right? But so the point I want to make is that it amounts to this: that classifying the original problem depends on writing down, being able to describe all of the pairs of one forms, eta 1, eta 2, and 4 functions, P1, P2, P3, P4, that satisfy these equations. That's what it depends on. And conversely, if you're given those satisfying these equations, you can reconstruct theta, and hence by Cartan's fundamental lemma, you can get the surface, and therefore you can get M. Because once you know the surface, its normal bundle gives you M3. Right. Unfortunately, these equations, you can think of it as an exercise in differential algebra if you want. You have your algebra is generated by 2 one forms, eta 1, eta 2, and 4 functions, and they're required to satisfy these identities. And the question is, how do you know whether or not there are such forms, and how many there are up to diffeomorphism? The way you tell, it turns out, was discovered by Cartan back a long time ago, back in the early part of the 20th century. And the answer is it has to be true. See, this formula, if you're thinking in terms of differential algebra, this formula tells you know the differentials of the things generating your algebra, right? And now you want to know, is there an algebra with those properties? Cartan says, yes, there is if d squared is 0, right?
What's d?
D is the exterior derivative.
But d squared is 0.
But see, you might be able to, you could write down formulas like this, and it might not be that d squared was identically 0, because, see, you have the formulas for d, so now you can compute, for example, what is d of eta 1. You can just figure it out using the rules for exterior derivative, because you know the derivative, the exterior derivative of P1, right? And sure enough, it turns out that for eta 1 and eta 2, P1, P2, and P3, it turns out that d of that is 0. These formulas actually satisfy d squared equals 0 for those things, but not for P4. It turns out.
So what's the statement?
The statement is that using these formulas, this capital F has the property that if you just formally compute the exterior derivative of the exterior derivative of eta 1, eta 2, P1, P2, and P3, you'll get 0. I mean, you can see that, for example, you could compute.
But then what?
Okay, so that's true, but unfortunately it's not true that this F implies that d of P4 is 0. In fact, what you get is some rational function of A, C, P1, P2, P3, P4 that does not necessarily vanish.
No, but what's r?
I haven't told you what R is. R is a complicated rational expression in A, C, P1, P2, P3, P4.
A certain r.
There's a certain R. There's a certain R that so that equation is true. And so what that means is that there can't be a solution to these equations. There is no algebra with that property except in the subset where this R vanishes. So you can.
You have r that equals 0. Now you're saying.
No. Yeah, so this is some rational expression in these quantities, and it has a 0 locus, right? And what we're saying is that we're saying that you can't arbitrarily specify P1, P2, P3, P4. They have to satisfy, they have to lie in this locus, otherwise the algebra doesn't exist. I mean, this differential algebra doesn't exist.
Yeah, that we must have.
So we have to have this, but we also can we can also apply the exterior derivative to this expression, and we'll get more things involving AC, P1, P2, P3. You know, there'll be, when we take its exterior derivative, we'll get another rational expression in these guys times eta 1 plus another rational expression times eta 2, and they will have to be 0 as well.
So they have to satisfy three relations.
Now 3 relations, right? And I haven't said anything about these things because they actually have dozens of terms, and these have 30 or 40 terms apiece. Turns out.
Well, the arguments inside r are functions.
Yeah, those are functions, or you can think of them as unknown variables, or you can think of it. I mean, what we're trying to do is cut out the locus in which d squared will be 0. That's what we're trying to do, and we don't want to make eta 1 and eta 2 dependent because they have to be independent forms on the surface, right? And so when we differentiate these things, we keep getting things like this. So, and if you sit down and try to actually solve those equations by hand, it's a nightmare. They're really, really complicated. But it turns out you're not done. It turns out that, after the smoke clears, and I'll say what you have to do to prove this, the proposition is this, that if d squared is going to be 0, then either h1 and h2 are constant, in which case it's isoparametric, or a has to be minus 9/4 and p4 has to be 0. That's the only way it can happen. And if you actually plug those in, a is minus 9/4 and p4 is 0, then r vanishes. R vanishes identically in that case. That's actually a sublocus of the 0 locus of r, which is quite complicated. But how do we get there? It turns out that what you have to do is you differentiate r, you get the R1 and R2, you differentiate R1 and R2, and you get R11, R12, R22. You differentiate that. You actually have to differentiate out 4 times. And then you have this big system of algebraic equations that you don't know what to do with, but Maple knows how to apply Grosvenor. And you can apply Grosvenor to this, and Grosvenor will tell you that these guys and their derivatives all vanish only if h1 and h2 are constant, or this is true. I would love to have an argument that works by hand, but so far, no idea. But
what's the conclusion?
The conclusion is that the only way these things can exist is, the only non-trivial case is when a is minus 9/4 and p4 is 0. So in other words, plug those in, and now you have something that satisfies.
A.
Oh, A is the product of the H1 and H2, right? So, so this is one of these cases where I can see why in particular Tsukada couldn't answer this question back when he was working on this problem, because he just couldn't do the algebra. And of course, I can't do the algebra, but Maple can. So,
Grosvenor bases are very hard to compute and work with.
Right. Yeah. In fact, a machine. Most machines, when you run this and apply Grosvenor, it runs for quite a while before it actually spits out what the Grosvenor basis is. And then it turns out that if you go down to the first few terms, depending on how you order the terms, but the first few terms are somewhat complicated. But then I think it's the 4th basis element in the basis has to be minus 9/4. Yeah, just, this is one of those cases where, it's not AI, but it's a computer-assisted proof that as far as I know, no human could have done, and I wouldn't have been. In theory you could, but maybe it would be like somebody computing by hand the 1,000th decimal place of pi or something like that. You spend 15 years doing it. And so, but anyway, once you get this proposition, and I realize I'm going to run out of time if I'm not careful. Once you do this, it turns out that d squared is 0 holds identically for this system. I've gotten rid of P4, I've set A to be minus 9/4, and now this thing satisfies d squared is 0. And so by Cartan, there exists such a solution, so it satisfies, so the theta will exist, and the surface will exist, and so on, right?
So that's the three-dimensional surface.
It'll produce a hypersurface, which is a unit normal bundle of a surface in S4.
And what's the surface?
Well, we'll come to that. Right.
Oh,
Yeah.
hiding it from
Second time we've asked.
Yeah, that's right. Yeah. What surface is it? Well, because surely if well, the interesting thing is that when you look at it, so Cartan's theorem tells us that you can specify P1, P2, P3 at a point, and there'll be an open neighborhood of the origin on which the forms eta1 and eta2 and functions P1, P2, P3 are defined, and they equal those the given values Pi bar at the center, and correspondingly there'll be a germ of a surface whose unit normal bundle is non-homogeneous but curvature homogeneous. If you count carefully, what you find out that what that tells you is that there's actually, because it's not curvature homogeneous, because it's not homogeneous, the different points of the surface will give you different germ values will give you different values for the P's. So they sort of, that every different initial value of the P doesn't give you a different surface. But it turns out that they all fit into a one-parameter family of surfaces. So here's the theorem, proved last year. The paper appeared this year. For whether C is plus or minus 1, there's a one-parameter family of non-homogeneous, curvature-homogeneous hypersurfaces that are mutually non-congruent. And the Ricci curvatures of their metrics, there they are. They're constant. That minus 9/4 shows up. And every connected non-homogeneous curvature homogeneous hypersurface is congruent to an open subset of one of these. There's exactly a one-parameter family of these. So what do these surfaces look like? That's what I'm coming to. Here's the thing that surprised me. None of these things are complete. There's this parameter lambda that's greater than or equal to 0, and if it's positive, then the surface has only discrete symmetries. It doesn't even have any continuous symmetries at all. So they're not homogeneous. They're not anything like that. But when lambda is 0, you actually do get at least a one-parameter symmetry group, it turns out. And
are they locally homogeneous?
No, none of them are locally homogeneous. They're, at most a one-parameter symmetry group. And the lambda 0, when lambda is 0, it actually is an open subset of an algebraic variety, and in fact, it's very simple. It turns out it's the image of an analytic map from the 2-sphere into the 4-sphere. So it looks like it's a copy of the 2-sphere, except that so the 2-sphere is given by u squared plus v squared plus w squared is 1, but you'll notice in the explicit formula that I give, w appears to the second power and the third power, which means that this is not an immersion. What happens is that the surface, our 2-sphere, S2, gets mapped into S4 as a kind of a ravioli. There's the equator w equals 0 is a crease, and you get this sort of crease surface, and the northern hemisphere maps up, the southern hemisphere maps down, and it's sort of like I said, it looks a bit like a ravioli. The boundary curve where w is 0 is sort of like uv, 2uv, u squared minus v squared. Up to scale, it's a kind of it's
Clamshell.
That's right, yeah, and it fits together. And it's clearly algebraic. I mean, the image obviously is some algebraic, but it's a singular surface. That's the M0. And
Not isoperimetric.
it's not isoperimetric, no. The H's aren't constant. The H's are definitely not constant. With a little more work, we didn't even know this existed because we found out that when lambda was 0, there was a one-parameter symmetry group, so we could say, oh, so it's got a symmetry. We can divide out by the symmetry and reduce it to a one-dimensional problem, and we could integrate the ODE. Great. However, when lambda is positive, there's only discrete symmetries. There's no continuous symmetry, so you can't divide out by circle action and reduce the dimension. But we were able to prove that even for positive lambda, the surface is always the image of an analytic, is always the image of a two-sphere, and it always has a crease along the equator.
A what?
A crease like this, where the thing drops rank, but the crease gets more and more curved as lambda goes up, and the final mystery is that when lambda is not 0, we don't know whether or not this is algebraic. Lambda equals 0, it's clearly algebraic, but since we can't integrate the equations explicitly, we don't know whether or not the surface is algebraic. There's a natural guess as to what the degree of the surface would be, and you can, which the natural guess comes from certain considerations about the discrete symmetries, but then you check out and find out that the natural guess is wrong. It's not that, it's got to be higher degree than the natural guess, but we don't know how high. Probably, the lowest it could be is something like degree 12. But they exist, and the reason we've never seen them is that they don't have much symmetry, or practically any symmetry. But these were the final unseen examples of curvature-homogeneous hypersurfaces. They're sphere bundles over creased surfaces and creased two spheres in S4. I think and I'm just about done. I think the interesting thing about this problem is that it turned out to be amenable to tools that we had, but not tools that we could actually practically do until we got symbolic computation. And to me, the really mysterious, kind of weird thing is that it didn't turn out to be anything we could have guessed. There's no. It's not some low-degree surface or hypersurface or anything like that that we could have stumbled on by accident, or anybody could have written down as an example. But at least now we know it's there. Anyway, I think the lesson for the future is that a lot of these classification problems that people have struggled with over the years, maybe even though they're easy to formulate and clear natural questions, the actual techniques to solve it may be, we may only now have the tools we really need to actually answer those questions. And what AI will do eventually, who knows? But I think computer-assisted proofs are, pretty much here to stay, even in differential geometry. Okay, so I think that's all I wanted to say. So thanks.
Any more questions?
Yeah.
So now you've constructed at least one of these explicitly, maybe the lambda zero ones as well. Can you explicitly get this mapping between the tangent spaces that is in the definition of curvature homogeneous?
Yeah.
Check that it really is the right, doesn't it?
You could actually check, of course, because this has a one-parameter symmetry group and it's two-dimensional. That means there's really only a one-parameter family of non-congruent points on the surface, right? And so all you have to do is go along a curve transverse to that and check that they work. And you can easily write it down. You can easily compute it by hand that it works. Right. But how you would ever guess it, I do not know. Right. Yeah.
So, supposing you knew this specific example where lambda is 0, is it possible to find the other solutions without, perturbing off of that just for other values?
Yeah, it's an interesting question because I know sort of what happens in the perturbation, in the sense that it turns out that there's only in the rotationally symmetric case, it turns out there's only two places where the minimal curvature vanishes, and that's the images of the north and south poles. That is where U and V are 0. And I know that when you perturb lambda to be positive, those minimal points split, each one of them splits into two minimal points. And they're like foci of an ellipse, and there's a sort of a parameterization in terms of ellipses on the sphere, elliptic parameterizations, where you can actually locate those points by finite tools. In other words, you can know them exactly without having to solve differential equations. But beyond that, I don't know. I mean, I put some effort into trying to find the algebraic equations, but like I said, I don't know whether it's algebraic.
But for the PD itself, if you just wanted to show, maybe even just for small values, the existence of solutions,
well, if you write down the differential equation for a deformation to remain curvature homogeneous, that's now an overdetermined PDE system for that. And so you basically almost have to repeat the process that we did here to figure out what the deformation vector field is. But you can infinitesimally write down the deformation vector fields. Yeah. Yeah, it's mysterious, actually. But I mean, we shouldn't, in some sense, we shouldn't expect everything to be, just because they're almost unique, we shouldn't expect them to be algebraic. If you look at, for example, the minimal surfaces in the four sphere that are invariant under a circle action, the vast majority of those are not algebraic. They're actually, you can prove that they're not even elementary functions. They're elliptic functions or worse to actually try to parameterize those things. Yeah, right. So it could be that they're just not anything more to know, but it's kind of disappointing that that we can't answer the question one way or the other at the moment.
Did you say what this lambda was, or did you
I didn't say what the lambda is, but the
you seem to like it?
basically it's not completely easy to describe, but and maybe that belongs to a different. I mean, you can tell which values of in the set of P1, P2, P3, you can write down. What we're saying is that basically the P1, P2, P3 space is foliated by the images of this one parameter family, and it turns out you can actually write down an expression in P1, P2, P3, or one form in P1, P2, P3 that turns out to be exact, and it's different. And lambda is that lambda as a function, its differential is that expression that gives the same all the points with the same that belong to the same surface. Right.
Maybe it's a technical question. So this P1, for instance, you could determine it because d eta 1 is a 2 form, so it's a product of omega 1 and omega 2.
Right. Yeah.
So P1 is just some derivative along one of the directions of H1.
Yeah, that's right. Yeah.
Doesn't that shrink the system a little bit or reduce it?
Well, in fact, I reformulated the unknowns. I could have taken the unknowns to be H1, H2, H1's derivative in one direction, H2's and stuff like that. Then I would have had to write down a horrible expression for P1 in terms of H and its derivatives. and I didn't want to do that. This seemed like the closest way to explain how we're applying Cartan's theorem. You write down a potential differential algebra, and you check whether or not d squared is 0. And you want to write it down in terms of the generators to try and, so that you can, the simplest generators you can. And so, that was a pedagogical device, right? Yeah.
Can you say what the differential algebra is? Satisfies d squared is 0, right?
Yeah, it satisfies d squared equals 0. It's a, I'll say it this way. It's a subalgebra of the differential forms on the two-sphere, and how do I want to say it? It's analytic differential forms on the two-sphere. The expression f is rational in its variables, but well, you can see, you can almost see what kind of formulas they look like a little bit by seeing what kinds of things these, since we have this one explicit, you can actually go back and compute what eta 1, eta 2, and P1, P2, P3 are. You could do that in this particular case, and you'd see rational expressions in U, V, and W.
U, V, and W is 3 space, but the two-sphere is?
Right, yeah. Of course, U, V, and W are actually constrained to lie on the two-sphere, right? So it's some subalgebra it's some subalgebra of the differential forms on the two-sphere, right?
Is there a way of seeing that this is going to end up being a two-sphere without solving the problem?
No, in fact, I didn't explain how I knew that it was going to be a two-sphere. That actually turns out to be kind of subtle, and in fact, in our paper, we don't prove that. I'm responsible for writing part 2, where we actually proved that. So,
Confession.
yeah, confession. That's right. Well, we admit that we admit. I mean, we say we're going to do it, and then, but we didn't do it in that paper.
Claim.
That's right. We claim that it's true, and I'm responsible for writing part 2 that will actually prove that. Right. It's a I've got about 20 pages written about this. It's surprisingly subtle because you have to deal with certain apparent singularities that turn out not to be singularities, but proving that they're not singularities is because you want to show that it extends over the two-sphere because Cartan's theorem is very local, right? It only proves that there's a germ of a surface, but how do you integrate the germs to see what the global topology is? And that's the part that still needs work. I still need to finish writing it up.
So this is a soft comment question, sort of. So, like those functions there are not algebraic, but they're Nash, namely they satisfy algebraic equations.
Right, that's right.
Right?
Yeah.
So do you know your surfaces have Nash structures? They're not algebraic, but they're analytic, but they're functions that satisfy algebraic.
I do not know that they satisfy algebraic equations.
What?
Right.
What?
I do not know that they satisfy algebraic
So
equations.
that's a question you could ask.
Right. Yeah.
And then
Yes, sir.
that you used the word elementary before.
Right.
There is this differential Galois theorem.
That's right. Yeah.
You
Yeah.
have to-
And I mean by I'm without defining it, I'm using that notion of elementary. Right. Yeah. When I say that I don't know that that the surfaces with lambda positive are actually elementary functions. But like I said earlier, there are plenty of global minimal surfaces.
They're part of a bigger notion differential Galois.
Right, yeah, that's right, yeah. That's right, and there's this extension, right, yeah. And like I was saying, the circle, the rotationally invariant minimal surfaces in the 4 sphere, minimal hypersurfaces in the, minimal surfaces in the 3 sphere, those are not, they are not parameterizable by elementary functions. You can.
What about higher Galois?
That's a good question. I don't know. I mean, Yuval's theorem tells you when things are elementary or not, right? But then the next step up, I don't know. I just know how to prove that they're not elementary functions. Right? Yeah, that's an interesting problem already. Yeah.
Let's do the speaker again, and then if you have more questions, stay over.
Yeah. Right. Okay. Thank you. Thank you for your attention. Right. Yeah.
Are you going to be around in a little while?
Oh yeah. I'm here for.
I had one last.